All right, let's see how long this one's going to take us. We want to try to get through our practice final. And so, once again, I apologize for the smallness of the font here. Uh, you're meant to print this off and follow along, or you could follow along on the computer. It's on our class website. Okay, so let's see how we do here. Suppose that a hiker's elevation in feet is modeled by f of x equals 30x squared plus 50x after x hours. What is the average rate of elevation gain of the hiker between time 1 and time 2? And what is the instantaneous rate of change at 1.5? Okay, so part A is to compute an average rate of change. Part B is to compute the instantaneous rate of change. So let's do that. Oops. So 1A, let me get that to make sure you can see that. Our function here was 30x squared plus 50x. And we want to compute, for part A, we want to compute the average rate of change from 1 to 2. Okay, so I need to know what the functional values are there. And so at time 1, it looks like it's 80. And if I plug in a 2, I get 30 times 4 is 120, plus 100 is 220. Okay, so now the average rate of change is going to be our f of 2 minus f of 1 divided by 2 minus 1. And so we can read those off. 220 minus 80. Oops, 220 minus 80 divided by 1. And I believe that's going to be 140. Okay, for part B, the instantaneous rate of change is given by the derivative. So that's going to be 60x plus 50, and we want to evaluate that at time 1.5. Okay, so let's see, if I do evaluate that at 1.5, I get, what is that going to be, 90 plus 50 is 140. Okay, so in this case, they happen to be the same. Okay, let's see, part 2, or number 2. Let's check it out real quick. A water balloon has a height modeled by this function, where height is measured in feet and time in seconds. So just as a quick note here, minus 5t squared plus 20t plus 25 is a nice parabola. What does the parabola look like? Well, I don't want to write on that, but the parabola is going to be opening up downward, right? I'm not sure what the times are for the intercepts yet, but it's a parabola that opens down. Okay, so we want to find the maximum height. So you're probably going to guess, right? The maximum height is going to be at the vertex. Give a function for the velocity. If this is the height function, then the velocity is going to be the derivative of that. And finally, when the balloon hits the ground, how fast is it going? So we know what the velocity function is by part B, and so we'd have to set f of t equal to 0 to find the time at which we hit the ground. And so if we find the time value for that, then we can plug it into our velocity function to find out how fast it's going. Okay, so that's the plan of attack there. Let's go ahead and write down our function, minus 5t squared plus 20t plus 25. Minus 5t squared plus 20t plus 25. Good. So part A was the maximum height. So that's at the vertex. You could use the minus b over 2a formula, or you could just take the derivative, set it equal to 0. Minus 10t plus 20, that's easy enough. T equals 2 is the location of the vertex. And then if we plug in time 2 into our original function, we'll get the height. So if I plug in 2, let's see, minus 5 times 4 is minus 20, plus 40 plus 25. Let's see, that's going to be a 45. Okay, so that's 45 feet at 2 seconds. So our maximum height is 45 feet and it occurs at 2 seconds. B. What's the velocity function? That is our derivative. Oops, I put in an x instead of a t. I mixed those up. Sorry about that. Velocity is our derivative, which is minus 10t plus 20. Good to see. When it hits the ground, what's the speed? Okay, so I need to figure out when the balloon hits the ground. So I'll set minus 5t squared plus 20t plus 25 equal to 0, and I'll solve that for t. Notice that I could simplify this by dividing by minus 5. And so if I do that, I would have t squared minus 4t plus minus 5 equals 0. And so this is a lot easier to work with, right? Can you factor that? Looks like t minus 5 and a t plus 1, huh? So that'd be minus 4 and minus 5, yep. And so therefore, we get that the balloon is at the ground level at t equals minus 1 and t equals 5. And so we're ignoring the negative time, right? So we'll just take time 5. So at time 5 we hit the ground, so therefore we plug the speed at which balloon hits the ground. Let's see, 5 times 10 is minus 50, plus 20 is minus 30. So minus 30 means it's heading to the ground at 30 feet per second. So the speed is going to be 30 feet per second. Or you could say the velocity at time 5 is minus 30 feet per second. Okay, where the negative, oops, I went off the page. So that's minus 30 means you're heading for the ground. Good. So that's number 2. How about number 3? Cup of coffee, 180 degrees. Place it in room, 72 degrees. After 10 minutes, the temp is 135. Use the model for heating, cooling, find out when the temperature is 100. Good. Let's write down our data. So let's see if I can keep on the screen this time. So my data is that the coffee starts at 180 degrees. The room is 72 degrees. And after 10 minutes, the coffee is 135 degrees. Okay, and then we want to find when the temp is 100. Okay, so there's 2 possible models that you can use. It doesn't matter which one. The one we were using in class, I think, is a times b to the t plus c. Or, I'm going to go ahead and write it on this one. You could write it as a times e to the kt plus c. Either one. Okay, so the idea here is that in either case, this first term, as t goes to infinity, the first term should go to 0 because it's connected to that exponential function. And so as time goes to infinity, right, your 180 should be heading towards your 72. So the only way that's going to happen is when c is equal to 72. So we can assume then that the room temperature is our value of c. And so right off the bat then we get the value of c. Good. And now we can use our initial condition that says that the temperature of the coffee starts at 180. And so that's at time 0. So if I plug in 0 here, b to the 0 is 1, and then e to the 0 is also 1. So in both cases, whoops, that was supposed to be 72. In both cases, we get that 180 is equal to a plus 72. Okay, so in both cases then the a is equal to 108. And so in this case we have y is 108 times b to the t plus 72. And in this case we have a is 108 times e to the kt plus 72. Good. So that's that piece of information, that piece of information, and now after 10 minutes, the coffee is 135. So in this model, we would have 135 is equal to 108 times b to the 10th power plus 72. And in this model, we have 135 equals 108 times e to the 10k plus 72. But in either case, you could solve for either your b or your e, right? Doesn't matter which one. And so I think here we ended up with 135 minus 72, 72 divided by 108 is b to the 10th power, right? So then you take the 10th root of that, and that's equal to your b. And then you do a similar thing over here, except you're going to run into some natural logs. So I'll just say over here, you should get that k is equal to minus 0.0539. Okay, and over here, you should get that b is equal to, what did I get? 0.9475. Okay, and so here we now have y is equal to 108 times 0.9475 to the t power plus 72. And over here we have y equals 108 times e to the minus 0.0539 t plus 72. Okay, and so lastly, you would just set your y equal to 100 and solve for the t. Okay, so see if you can do that. You should be able to get that t is about 25 minutes. 25.03 minutes. Sometimes it depends on how much you round off, but I'll leave that part to you. That's not too hard, just takes a little bit of time. Good. So that was kind of a long one. Let's see what's next. An observer is standing 20 feet from a building and notes that the angle between the ground and the top of the building is 72. How tall is the building? So let me keep this one's kind of a harder one to draw, so let me keep that around here for a second. Can we see that? The observer is 20 feet from a building. Here's my building. There's 20 feet. And of course, we're assuming that's at a right angle. There's the top of the building there, and there's my observer. Ground in the top of the building is 72 degrees, means that this one's 72. And so what's the height of the building? Well, this one's pretty straightforward. The sine of 72 degrees is h over 20. So therefore h is going to be 20 times the sine of 72. Good. This is number 4. And so if you compute that, what do we get? 19.02 feet. Good. I'll leave that for you. State the definition of the derivative. F prime of x equals the limit as h goes to 0 of f of x plus h minus f of x divided by h. Use it to calculate the derivative of x squared minus 1 over x. Now, we could do this all at once, but if you're smart, you will realize that you can do these separately and then put the two derivatives together. In other words, we can compute the derivative of x squared using our definition and the derivative of 1 over x using the definition, and then put those together at the very end. So I think it's a lot easier to do it that way than to try to do this all at once, because the algebra gets a little messy if you try to do it all at once. Okay, so let's go ahead and do that. So let's do x squared first. And so then my f prime of x is going to be the limit as h goes to 0 of x plus h squared minus x squared over h. We've done that one a few times. Limit as h goes to 0, then just multiply this out, FOIL this out. So that's going to be 2xh plus h squared minus x squared divided by h. x squareds cancel, the h cancels, and so you're left with 2x plus h. Now remember, when you're doing that, I'm getting kind of sloppy there, but you can only cancel factors. So remember that you can only cancel factors. Good. So that derivative is 2x, as we expected. Okay, so then for 1 over x, the f prime of x is going to be the limit as h goes to 0 of 1 over x plus h minus 1 over x divided by h. And now when we put these, let's see, I can bring this out as a 1 over h, and then I want to get these together as with a common denominator. So let's see how that would work. That would be the limit as h goes to 0. I'm going to have that 1 over h sitting here. And then for this fraction, I'm going to multiply the first fraction by x over x, and the second one by x plus h over x plus h. And so I'm going to end up with x minus x plus h divided by x times x plus h. Okay, so that's how I get my common denominator, right? Oops. And of course I'm running off the page. Good. And so now on the top you can see that the x's are going to cancel, the minus h is going to cancel with that guy, and so you're just going to be left with the limit as h goes to 0 of minus 1 over x times x plus h. And now when you put in x equals 0 down here, you just get minus 1 over x squared. Good. And so now overall then, we see that f prime of x is going to be 2x minus, that's that, minus 1 over x squared. Good. All right. Oh, and of course I ran off the page. Okay, so that was number 5. Gosh, it's kind of long. Next. Number 6 is actually doubled up. Sorry, I didn't catch that. So these are basically just asking for antiderivatives, right? So if the derivative is 3x squared plus 1 over x, what was the original function? I think we see that that would be x cubed plus the natural log of x. X cubed plus the natural log of x. Okay, so we won't write that down. For 7a, the derivative of x squared plus x, of course, is just 2x plus 1. For b, oh, maybe we should start writing those down. Let's see, for b, e to the x squared plus x is going to be f prime of x is e to the x squared plus x. That's the derivative of the outside function with the inside function stuck in. And then you multiply by the derivative of the inside function. And then 7c, the derivative of the cosine is going to be minus the sine. And then put your inside function in there. And then multiply by the derivative of the inside. And we've already computed that. That's e to the x squared plus x times the derivative of the inside, that inside, which was 2x plus 1. Good. And then number 8 is similar. F of x equals sine of x squared. What is f prime of x? Cosine of x squared times 2x. What's f double prime? Derivative of cosine is minus the sine, so that's going to, and then we put in the sine of x, or we put in the x squared, and then we multiply by 2x, but then we also have a 2x there, so that's going to be 4x squared altogether, plus the cosine of x squared, and then the derivative of 2x would be 2. Good. Hey, we made it without running off the end of the page. Good. Let's go to number 9. How are we doing on time? Oh gosh, we're at 20 minutes already. Let's see if we can finish this guy up here pretty soon. Find the equation of the tangent line. Oh, that's pretty straightforward. Equation of the tangent line. So number 9, remember that we have y minus f of a equals f prime of a times x minus a. So let's see, a is equal to 9. F of a is the square root of 9, which is 3. F prime. of x is equal to 1/2 times x to the minus 1/2. And so remember that that's 1 over 2 times the square root of x. I wrote it this way so it's easier to see what's going to happen when we plug in the 9. You're going to have 1 over 2 times 3, which will be 1/6. So if we evaluate that at x equals 9, we get 1/6. Okay, so now our point is the 0.93, and our slope is 1/6. So we have y minus 3 is equal to 1/6 times x minus 9. Good. And now when we plug in 8.9, we have a difference of minus 0.1, and then you have to multiply by 1/6 and then add 3. Okay, and so if you do that, you get approximately 2.98 something something. Let's see if I can find that. Where I did then 2.9833. And by the way, that is very close to the square root of 8.9 if you plug that into your calculator. So our approximation is very good there. Good. Number 10. Y cubed minus xy equals minus 6. Find dy over dx. So remember, this is telling us that y is a function of x. So therefore, when we differentiate, we're treating this like it was f of x cubed, right? And so the derivative would be 3 times y squared times dy over dx. And then when we differentiate x times y, we want to use the product rule. So the derivative of x is 1 times y plus x times the derivative of y. Okay, and then the derivative of minus 6 is 0. Good. Now, when we simplify this, we'll get 3y squared minus x dy over dx is equal to, I'll bring the y over to the other side. So the dy over dx is equal to y over 3y squared minus x. Okay, and then the question asks us to evaluate, once you find dy over dx, we want to find the equation of the tangent line at the point 7, 2. Okay, so we have the point. We know the slope then. The slope is going to be, let's see, 2 divided by 3 times 4 is 12 minus 7. Is that 5? 2/5. So we get y minus 2 is equal to 2/5 times x minus 7. Good. All right. What's next? Draw a curve that is bounded for all x, increasing and concave up for x. Okay. So let's think about it this way. We know that, so here at time a, we want our derivative, f prime to be positive, and f double prime to be positive. And over here we want our derivative to be negative and f double prime to be positive. Okay, so if we just draw a sketch of that, right, increasing and concave up would look like that maybe, and then decreasing and concave up, you could make it like that. So then the question, of course, is how do we know that the function is not differentiable at this point? You know, the way we've drawn it, there's like a sharp point here, but that's not necessarily the case, right? So the way to kind of think about this, I think, is to take a look at your derivatives, right? So if I just plot the derivative function along the graph, if I want to go from positive to negative, it would have to look like this. But notice that this means that f prime is decreasing. Can f prime be decreasing? No, f prime cannot be decreasing because f double prime is greater than 0. So these two facts are contradicting each other, right? Because if f double prime is positive, that means f prime is increasing, not decreasing. And so these facts are contradictory. Therefore, you cannot have a picture like this. Therefore, you're going to have a break in your graph. Your function is not going to be differentiable at the point A. You're not going to have a nice function going from positive to negative like this, because you can't have a decreasing function, right, if your second derivative is positive. Okay, so that's why you end up with this break. Your break is going to look like this. It's positive on this side and then negative on this side, but your derivative is always increasing, right? You're increasing, but you had to break there. So that's how we get that answer. So that's a little bit of a technical question, number 11. But the first part was valid. You should be able to draw a sketch with these properties, but the reason why f prime is not differentiable at x equals a was a little bit more tricky. Good. Where are we? Oop, I put down the wrong page. Here we are. The volume of a cube is increasing at a rate of 10 cubic centimeters per minute. So therefore, we have a cube with length s, so volume is s cubed. And so therefore, dv over dt is going to be 3s squared ds over dt. And we're told that the rate of change of the volume is 10 cubic centimeters per minute. And we're asked to find ds over dt if our s is 30. Okay, so that'll be straightforward, right? Just plug everything in. So it's going to be 10 over, let's see, let me go ahead and compute that real quick. Okay, so 30 times 30 will give us our 2700 here, and then I divided that out. So our answer is going to be 10 over 2700, or 1 over 270. Okay, so that's going to be our ds over dt. The second part of the question asks about surface area. So our surface area, let's just call it S. Oh, I've already got how about A? Surface area, how many sides are there to a cube? 4 sides, and then on top and the bottom gives us 6. So each area is s squared, so therefore we have a 6s squared is going to be the surface area. And so dA over dt is going to be 12s squared, or 12s ds over dt. And so now we want to find dA over dt, find this, when our s is 30 and our ds over dt was 1 over 270. Okay, so whoops, and of course I went off the bottom of the page. Okay, so your ds over dt is going to be, or dA over dt is 12 times 30 times 1 over 270. I'll let you compute that number. Good. That's number 12. We're getting there. We're about a half an hour mark. Let's see. So number 13 is pretty much a straightforward L'Hopital's rule. So maybe I'll just go ahead and put it right on here. The limit as x goes to 0 of this expression. If I plug in x equals 0, I get e to the 0, which is 1 minus 0 minus 1, gives us a 0 on the top and a 0 on the bottom. Okay? And then if I use my derivatives now, that's going to be the limit as x goes to 0 of 2e to the 2x minus 2x divided by 3x squared minus 1. Good. Now, what happens when I approach the value x equals 0? The denominator will go to minus 1. And so now L'Hopital's rule is off limits. What happens in the numerator? You end up with a 2 times e to the 0, which is a 2. So we get a 2 divided minus 0, by the way. So that's going to be a 2 over minus 1, right? So that's going to be a minus 2. Good. So number 14, we'll just kind of make a sketch here. We want to max c squared times s such that s plus c is equal to 24. Okay, so it's our choice as to which variable we want to substitute for what. It's probably easier to substitute for s. So we see that s is going to be 24 minus c. And so now I'm going to try to find the max of c squared times 24 minus c. Good. Now notice that 0 is a double root and 24 is a root of the original function of the cubic. And so if you were to think about what that's going to look like, at 0 you're going to have something like this, and then it's going to come down here at 24. That's what the cubic function is going to look like. And so this point right here, whatever value this is not symmetric like it is for a parabola when you're looking at a cubic. But this value, it looks like, is going to give us our max. And so the question was, be sure to justify why this is a max. Oops. And so we'll justify it as well, but geometrically you can see that you're going to get a max. Okay, so this is going to be 24c squared minus c cubed is our function. We can call it, well, I guess we're calling it capital F. So capital F prime is going to be 48c minus 3c squared. Set that equal to 0. Solve for c. So c equals 0. You can just kind of see that there. And then c is equal to 16, I believe. So you should double check me on that. Good. Now c equals 0 is not the one we're looking for. C equals 16 is the one we're looking for, because that's, we're trying to find the max out here. C equals 0 is actually our local minimum there. And so you can tell that by taking the second derivative test. That's going to be 48 minus 6c. And so if you plug in 16, we end up seeing that that's going to be negative for x equals 16. And so that means you're concave down, so it's like this picture. And so therefore we have a local max at c equals 16. Okay. Good. So what is c equals 16? C is the number of ounces of caffeine. So you got to have 16 ounces of caffeine. Oop, EIN. And then what's S? Oh, number of hours of sleep. So what's S going to be? Sleep. If C is 16, sleep is 24 minus 16. And, is that equal to 8? Oh, psh. Who gets 8 hours of sleep? 16 ounces of caffeine and 8 hours of sleep will give you your max. Good. We'll take a look at this last problem real quick. I don't know if we need to spend a lot of time on it, but I just wanted to really set things up for you so you can kind of see the technique that we're using to solve that one. So here's the function 48x plus 54, and we want to find where f is increasing, decreasing, concave up, concave down. We're not going to sketch a graph of it. Also inflection points. Okay, let me recenter myself here. Good. Now, increasing and decreasing is where the first derivative is positive or negative. So I need the first derivative, and that's 3x squared minus 18x minus 48. And just for fun, you could go ahead and factor out that 3. That's 3 times x squared. It just makes it easier to factor later. Minus 6x minus 16, is that right? And the factors of 16 are 8 and 2, right? So therefore factored, this becomes, there's an 8 and a 2 in there. How shall we write them? Minus 8 plus 2? Okay, so therefore the zeros of the derivative are at negative 2 and 8. So critical points are negative 2 and 8. Good. And notice that this is a parabola that opens up, right? And so therefore, if these are our critical points, right, if you just draw a sketch of your derivative, negative 2 and 8, right, it's going to look like this. So therefore, the derivative is positive here, negative there, positive there. So here, the function is increasing. Here, it's decreasing. And here, it's increasing, right, for the original function. Good. Similarly, let's go ahead and take the second derivative. I guess we could go ahead, 6x minus 18. 6 times x minus, what is that, x minus 3. So x equals 3 is where the second derivative is equal to 0. And also, we don't really need a full number line for this, right? If you're at 3, right, if you're below 3, the second derivative will be negative, right? So like 0 minus 3 is a negative number. And then positive on this side. Concave down, concave up. So we each have a change in concavity at x equals 3. And so this is our inflection point. Good. Now we know where the function is increasing, decreasing, concave up, concave down, and an inflection point. Good. So the point here was that I wanted to show you how to use those sign charts, right? That was the main feature of that section. Good. That was the final exam sample in 37 minutes. Hey, that was pretty good. All right. I think we're ready. If you do have questions about anything, let me know. Otherwise, I'll see you later.